Donc, on peut recommencer avec le deuxième groupe pour aujourd'hui, qui est le groupe du Colegiul Emil Racovita de Cluj, en Roumanie, qui va nous présenter un sujet en anglais. Ce sujet leur a été proposé par Yves Papeguet, donc qui s'intitule « Construction d'un solide à 5 faces ». La responsable de l'atelier est Ariana. Donc, juste pour préciser pour le public, donc l'exposé sera en anglais, mais nos élèves sont en très bon niveau d'anglais. Ce sera parfaitement compréhensible. Et n'hésitez pas à poser toutes vos questions en français ou en anglais. J'essaierai de les traduire du mieux que je peux si elles sont en français, afin de les leur poser. So, it's okay, guys. We are listening to you. Thank you.
Thank you. My name is Andrei.
And my name is Misnia.
And as I was saying, we will present our findings on the research topic number 7, which is the construction of a 5-sided solid. We have worked on this research topic together with our colleagues from Emil Racovita National High School in Cluj, as well as from the Lycée Val de Durance de Pertuis, whose names you can see on this slide. The statement of the problem is whether it is possible to create a solid with 5 faces, for example, of which the probability of each face to be the same. And in the case of the 5-sided solid, the probability should be 1/5. So effectively, we had to create a 5-sided fair dice. Such dices already exist with 4 or 6 faces under the form of a tetrahedron or a cube, but we have proved that a 5-sided fair dice exists, and we have also generalized to an n-sided fair dice. We chose to analyze the prism as a possible shape for a fair n-sided dice because it has 2 polygonal faces and n-2 rectangular faces. In solving this problem, we had 3 approaches, which resulted in 3 different models: a theoretical model, a physical model, and an experimental model.
The theoretical model. As my colleague stated, we chose to work with the prism as a fair dice. A 5-sided prism is a triangular prism. And because of the prism's many symmetries, the 2 triangular faces will have the same probability of being rolled, and so will the 3 rectangular faces. We then continued to define the ratio of the prism R equals the base side length L over the height of the prism H, as you can see in the picture below. And with this ratio, we then defined the following correspondence. P mu of R is the probability that a prism of ratio R will land on either one of the 2 triangular faces after a random roll. Here, the constant mu characterizes the surface on which the die is rolled, because there is a difference in rolling a dice on a harder surface, for example, a wooden table, and on a softer, smoother surface. And we proved that this correspondence, P mu, is a function. For a 5-sided dice to be fair, the value of the function P mu of R must be equal with 2/5 or 0.4, because there are 2 triangular faces and 5 faces in total. So now we only needed to prove that there exists an R for which P mu of R equals 0.4. And for this, we proceeded to state and prove 4 properties of our function P mu. Firstly, the function is strictly increasing. Secondly, the limit as r goes to infinity of P mu of R is equal to 1, and the limit as r goes to 0 of P mu of R is equal to 0. Then the function P mu is continuous, and finally the function is surjective. The function is even bijective, but we are interested in the surjective part. And in the picture below, you can see a graph of a possible function P mu. Keep in mind that this is not the graph of our function, it is only a possibility for the graph. And now, since the function is surjective, it follows that there is a value R0 such that P mu of R0 is equal with 2/5 or 0.4. and thus any prism of ratio R0 will be fair, will be a fair dice. However, the theoretical model was not sufficient to determine the exact value of the ratio R0, and thus we created a physical model.
The physical model. So using a probability distribution, we have proved that in order for the probability of the dice to land on a rectangular face to be equal with the probability of it landing on a triangular face, the two have to have the same potential energy. Here in the picture, we have a side view of the dice landing on a rectangular face on the left and on a triangular face on the right. Now, since the potential energy is proportional with the distance between the center of mass and table on which it stands, it then means that for the two to have the same potential energy, the distances have to be the same. We name them H1 and H2. So H1 has to be equal to H2, which after some geometric manipulation means that the ideal ratio R0 would be tangent of pi over 3, which is the square root of 3, approximately 1.73. But keep in mind that this is an ideal ratio because this model does not take the surface on which the dice is thrown into account. So to validate the theoretical and physical model, we conducted an experiment.
The experiment. Using a 3D printer, we printed 35 different dice, each with a different ratio. We did this by keeping the same base length of L, but varying the height. In the image on the left, you can see 3 different dice, each with the same base length of 2 centimeters, but with different heights. And with the help of a collaborative robotic arm or cobot, we then threw each of the 35 dice 1,000 times in order to get enough experimental data. This robot allowed us to roll a die 1,000 times in less than an hour and a half, which is much faster than a human ever could. The robot was also attached to a camera, which took photos of every roll, allowing us to count how many triangles and how many rectangles were rolled. On the picture in the upper right corner, you can see the robotic arm with the camera below, and on the TV there is a Python script which helped us run the robot and loop it so that it would repeat the same movement 1,000 times. And in the picture on the lower right, there is a sample photo that our camera took. In this example, the die landed on a triangular face. And after finishing all the 35,000 rolls, we then were left with the data presented in the table on the left, where the x-axis represents the ratio of the dice, which varies between 1 and 3.5. And the y-axis represents the number of triangles that were rolled, which also varies between 100 and 650. With these data from the graph on the left, we then graphed a possible function, p of mu, which is presented on the right. This is a piecewise function. It has 3 branches. The first 2 of them are second-degree polynomials, and the third branch, the green one, is composed of exponential functions and ratios of exponential functions. Using this function, we then proceeded to solve the equation to intersect this graph with the line of equation y equals 2 over 5, and got an experimental ratio of R0 experimentally approximately equal with 1.64, which is around the predicted ideal physical value of square root of 3 or 1.73. Therefore, our experimental model has validated our physical one.
Next, we proceeded to generalize the prismatic model. The function p of mu, which we used for our theoretical model, can be extended to an n-sided prism, and it will keep its properties as well as, and which means that it is also surjective in this case. The desired output is 2 over n in this case, for an n that is greater than 5, and not 2 over 5 as it was in the 5-sided dice. The physical model can be extended as well, as we can see in this picture. This would be the case for 7-sided dice, and the condition remains the same, that h1 is equal to h2, and that results in an ideal ratio R0 of tangent of pi over n minus 2, which validates the 5-sided dice. However, we have also discovered another possible dice, but this only works for an even n. It is the pyramidal model, which consists of 2 congruent regular pyramids stuck together at their bases, and this is supposedly fair because all of the faces have the exact same shape.
Yes, so in conclusion, a fair n-sided die exists for all n greater or equal than 5, but the ideal ratio, the experimental ratio, is dependent on the surface on which it is rolled. Moreover, for an even value of n, there also exists the pyramidal model, which my colleague described. Finally, we hope that you have enjoyed our presentation, and we would like to thank you for your attention. We are waiting your questions.
Thank you very much. I have to say that this presentation was really impressive, the different approaches and the results you found. It's quite impressive, so congratulations. We have a few questions from the public, so I will just translate what I say in French. Donc, je leur disais félicitations, que c'était très impressionnant les différentes approches qu'ils ont utilisées. Et donc, je vais donner les questions qui sont posées en anglais dans le chat en premier. So the first question is, does the contact surface really matter? Est-ce que la surface de contact importe réellement?
Yes, the surface does matter because I mean, you can try this at home. You can bounce dice on a wooden surface or on a paper, and it will not bounce back exactly the same. And while it might not be a problem in case critical, it will have different results on different surfaces.
Okay. Next question. So someone says, if I give you 5 positive numbers whose sum is 1, can you build a 5-side dice such that the probabilities for each side correspond to those numbers? Donc, est-ce que si on donne 5 nombres positifs dont la somme vaut 1, est-ce qu'on peut construire un dé à 5 faces tel que les probabilités pour chaque face correspondent à chacun des nombres?
This is a really interesting question because we based our approach on the fact that all the probabilities were equal, and that's why we used shapes that were symmetric, because in the case that you mentioned, in which the 5 numbers add up to 1 but are not necessarily equal, then symmetry plays no role in deciding what's the probability on landing on each face. We haven't thought of this, or it's
so
really
it's new topic of
generalization.
Okay, we have some more questions. For one dice, how many simulations have you run? Pour un seul dé, combien de simulations avez-vous entreprises?
I think we mentioned, yes, there were 1,000 per dice.
1,000, yeah, with the robotic arm, maybe, if I remember.
Yes, with the robotic arm. And in total, there were 35,000 because we had 35 different dice.
Okay. Next question. Is it possible, using the physical model, to find a theoretical formula for the function p mu? Est-il possible, en utilisant le modèle physique, de trouver une formule théorique pour la fonction P mu?
I don't think it really is possible to find the formula for the function, because the physical model predicts the case in which the probabilities are equal. So yeah, we tried to find an exact formula, but it did not match our the properties of the function that we found. And that's why we only use the physical model to find out the ratios at which the probabilities were the same, not different, for example.
Okay. Then, can 99 faces prismatic dice really be fair in practice? Est-ce qu'un dé à 99 faces de forme de prisme peut être juste en pratique?
I think that an appropriate ratio could be found for it to be fair. Again, it would depend on the surface, but I think it would be possible.
Yes, I think creating a 99 faces die, it would be more like a cylinder, because it would have two bases and there would be 97 different faces on the sides, and it would be really more like a cylinder than a prism. But in theory, yes, it would have to be very small. I think its height would be very small. Therefore, the ratio would be extremely large.
Okay. And the final question: why did you choose a triangular prism rather than a square pyramid, also five-sided? Donc, pourquoi avez-vous choisi un prisme triangulaire plutôt qu'une pyramide à base carrée qui a aussi 5 faces?
We have mentioned that we chose the five-sided prism because it has 2 triangular faces and 3 rectangular faces. It is more symmetrical than a pyramid, and it was much easier to work with. Also, I don't really think it would be possible to create it with a pyramidal model.
Yeah, I think it would be a bit harder to create, especially for the generalization, for only a pyramid. We did a generalization with 2 pyramids stuck together, but if there would be only one for n-sided die, then there would be 1 base and n-1 sides that would have the exact same shape. And it would be a bit hard to throw the pyramidal dice. The prismatic one seems more realistic.
Okay. So this is it. This was the final question. So I have to thank you again and to congratulate you, but because it was a really nice presentation, a nice talk. Afterwards, you answered very brilliantly to these questions. So I invite the public to go to the website of MATH.en.JEANS in order to discover your article. Donc j'encourage le public à aller voir l'article qui a été rédigé par ces élèves sur le site de MATH.en.JEANS. L'atelier de Cluj a rédigé un article à ce sujet. Et donc je les remercie chaleureusement et je les félicite pour la qualité de leurs travaux. Thank you very much, guys.